All right, so suppose that every time a car passes by a toll booth in one direction, another car passes in the opposite direction. Then the number of cars on either side of the toll plaza is constant. So here they have cars going this way and cars going this way. So under what conditions do physical and chemical equilibria, that's the plural word for equilibrium, occur? Well, when a physical change does not go to completion, the physical equilibrium is established between the forward and reverse changes. Equilibrium is a state in which the forward and reverse paths of a change take place at the same time. Balanced traffic at a toll bridge is a model for a system in equilibrium. When opposing physical changes take place at the same rate, the physical equilibrium is reached. When approaching chemical changes take place at the same rate, the chemical equilibrium is reached. So we're going to focus today on two types of equilibrium, chemical and physical. So a physical equilibrium, one example is liquid water left in a closed container eventually reaches equilibrium with its vapor when the rate of evaporation equals the rate of condensation. So in other words, there's water molecules that are in the water, but some of them escape into the air, and then it can cool and condense, and then eventually it's just it reaches a state where it doesn't evaporate anymore and it doesn't condense anymore. It does it equally. So liquid water in equilibrium with water vapor can be described by this equation: H2O, L, that's the liquid, and H2O gas. So what happens is it reaches a state of equilibrium. So many molecules evaporate within a certain time frame, and so many of those evaporated molecules turn back to liquid. The pair of arrows, this little double-sided arrows, shows or indicates the forward and reverse change happen at the same rate. It looks like an equal sign, but really, that's what it means. It means that liquid transfers or changes phase to gas, and gas changes phase to liquid equally. Okay? So let's talk about chemical equilibrium. When a chemical reaction does not go to completion, the chemical equilibrium is established between the forward and reverse reactions. Most reactions are reversible to some extent. A reversible reaction is a reaction in which the conversion of the reactants into products and the conversion of products into reactants can happen simultaneously. In the synthesis of sulfur trioxide, the forward reaction produces sulfur trioxide. Some molecules of the sulfur trioxide change back into the reactants by the reverse reaction. So here we have two molecules of sulfur dioxide, and then we add an additional molecule of O2, the diatomic version of oxygen, and they're a gas. And they change into two molecules of sulfur trioxide. There's three oxygens here, right? But some of these sulfur trioxides change back into the sulfur dioxide plus O2. During the chemical equilibrium, the reactants change into products just as fast as they change back into reactants. So they go back and forth. How do equilibrium systems respond to change? When a change is introduced to a system in equilibrium, the equilibrium shifts in the direction that relieves the change. The rule is first observed, and I can never pronounce these names, but that's what the rule is. It's known as that principle. So then, making the making of ammonia, I'm so tired, I haven't woken up yet, is the example of the process in which this famous chemist applied this principle. So we have nitrogen, N2, right, diatomic. Nitrogen travels in pairs, plus 3 hydrogen. Remember, hydrogen's diatomic. You guys know what I mean when I say diatomic? There are gases that don't like to be by themselves. They always travel in pairs. So nitrogen, hydrogen, oxygen, those are all diatomic molecules technically. So anyways, they change into ammonia and heat. They release a little bit of heat. So if the system containing nitrogen, hydrogen, and ammonia is in equilibrium, you can predict how the system will be affected by the changes in temperature, pressure, and concentration. Mathematically, you can figure that stuff out too. We don't cover that in this class as much as you would, say, an actual chemistry class. Temperature. In an equation for the synthesis of ammonia, heat is written as a product. The forward reaction is exothermic. In the reverse action, the heat is a reactant, so the decomposition of the ammonia is endothermic. So you go back and forth, even the heat. According to this principle, if you add heat to the system, the equilibrium would shift in the direction that removes heat from the system. The system would favor the reverse reaction, which is endothermic. By increasing the temperature, you would decrease the amount of ammonia. Pressure has an impact too. According to this principle, if you increase the pressure, the equilibrium would shift in the direction that decreases the pressure of the system. In order to decrease pressure, the system would favor the reaction that produces fewer gas molecules. By increasing the pressure, you would shift the equilibrium to the right, producing more ammonia. All this stuff weighs into it. Concentration. This principle tells you that if you decrease the ammonia concentration, this is on the reading guide, so pay attention. By removing ammonia from the system, the equilibrium would shift in the direction that produces the ammonia. In order to produce ammonia, the system would favor the forward reaction. So they're basically what they're saying is we can manipulate pressure or temperature or concentration to kind of break the equilibrium one way or the other. Okay. Operating an ammonia plant at relatively low temperature and high pressure, the low ammonia concentration maximizes the amount of ammonia produced. So when you make ammonia, it tends to want to reach a state of equilibrium. But if you want to maximize the amount of ammonia, you kind of force the reaction through utilizing a lower temperature, higher pressure, and low ammonia concentrations. In other words, they're removing the ammonia out of the concentration to maximize the amount that's produced. They're making it a mostly forward reaction. There's still going to be a little bit of backward reaction, but by making it mostly forward, they're going to produce more ammonia than decompose. Okay. So a couple questions. In a chemical reaction that is at equilibrium, which of the following is true? All the reactants are converted to products. The reaction stops eventually through some reactants remain. Forward and reverse reactions at the same rate. Yeah, that sounds about right. C? Yep, C. Here's the next one. In the chemical, now this is an important one. I believe this one is actually on the reading guide. In a chemical reaction, how could you shift the equilibrium towards water? In other words, how can we make this more of a forward, right? We're going to make water. How can we make this more of a forward reaction? We could increase the temperature. We could increase the pressure, decrease the amount of oxygen, add steam to the mixture. What do you guys think? I think I know B, right? Remember, increasing the pressure forces that to the right. A wouldn't work because we would need to lower the temperature, and the other option would be the concentration. Decreasing the amount of oxygen, we need to remove the concentration. So we would need to remove the H2O. We'd need to remove the water. And let's explain how that works. When I decrease the temperature, there's less energy to go backwards, right? Because we're releasing heat. That heat gets absorbed by the molecules in the process by lowering the temperature, so it makes it more forward. By increasing the pressure, I'm forcing things forward. Lastly, if I remove the water and there isn't as much water to be decomposed, I have a mostly forward reaction. That's it. That's all I got for you guys. The reading guide is posted in Canvas.